Okay, welcome back. Now that we have seen the idea of um, degrees of freedom, let's talk about another fundamental idea that always goes with that is the idea of kinematic constraints. So we saw this example before. Assume we have two particles for now in 2D space. So I have two particles, each one of them has 2 degrees of freedom. So in total, this is a 4-degree of freedom system. I need to know x and y position of particle number 1 and x and y position of particle number 2. Now let's connect them. So this is same system. Connect them with a rigid rod. Now with this constraint, I have removed one variable. So before the lengths or the distance between them could change arbitrarily, now I have removed that single kind of dimension or degree of freedom from the system. So now I have 4 minus 1. This is a 3-degree of freedom system. So I need to know the position of x and y and maybe the orientation or the angle of this system. And coincidentally, now I have created a rigid body in a 2-dimensional space, and we saw before that a rigid body in 2D has 3 degrees of freedom. So let's add another constraint. So still I have these two bodies, they're connected together. Now in this rod, let's pin the middle point to the ground. Now this becomes interesting because it shows the idea of constraint is not, again, similar to degree of freedom being not unique. The idea of constraint, how you view them, is not unique either. So with this, what I have done, I have constrained 3 variables. So what are those? So you can think of this as a system of 2 particles where now the distances d1 and d2 are constrained, and also the orientation between these 2 directions, so a theta. So I have constraint d1, d2, and theta. So that is one way we can think of this, the variables being constrained. The other one could be the total length between them and the position of the middle point. So x of center and y of center. These are the variables being constrained. So all of these are valid. You can think of them in different perspectives. But importantly, with this pin joint in the middle, I have constrained 3 numbers. And now, well, all I have left is 4 minus 3 equals 1. This system is 1 degree of freedom. As long as I know the rotation, the angle of that object, I can fully describe it. So this brings me maybe to another idea. So each kinematic object, if I will, such as a joint, does something to the system, reduces the degrees of freedom in a certain way. So a pin joint or a revolute joint, pin or revolute joint, if we are talking 2D, subtracts 2 degrees of freedom from the system. And in 3D, think about it, it subtracts 5. So it subtract this XYZ position of one joint, and also it restricts the axis of rotation. So you're only left with one degree of freedom of the rigid body left. So a pin joint in general is a let's see. Oh, don't do that. I'm struggling. Why does it do that? So pin joint in total is a let me put it there. Add missing, I hope that's a word, degrees of freedom. It only allows 1 degree of freedom in the system. Another famous one is a prismatic joint or a slider. It's a joint that let me draw it. Let me draw them as well. So this is what we show as a pin joint. A prismatic joint is something like that a body slides on another body. So it is exactly the same situation. So it's also one. Where did I go? Go back. It's also 1 degree of freedom joint. So what you can do, if remember we had this n equals k n, k being the degrees of freedom of each object. For a rigid object in 3D, that was 6 times the number of total objects, and then start subtracting this kc. So let's call it kc, the constrained degrees of freedom. By addition of each joint, you what other you have m, let's put m, you have m joints, and that one restricts this kc number of degrees of freedom. And you may have different types of joints, like, oops, that's a summation of all your joints that you have. You can start subtracting degrees of freedom according to the construct of the joint. So let's see what other good example I have. Maybe a screw joint, a screw joint. It is only valid in 2D, so this in 3D, so it doesn't show up in 2D. And a screw joint is a screw. So a nut, you can think of a nut that you turn it and it moves up. So it is a 2 degree of freedom joint, and it subtracts 4 degrees of freedom from the system. So all you need to do to describe that joint is, oh, no, that's actually a 1 degree of freedom too, is it? Yes, it is. So that one also is a 1 degree of freedom. So as long as you know the angle, how much your object has rotated, you know where it is in space, how much it has moved. Yeah, that's the one. And you can don't do this. Don't do this. Please. So there are all different kinds of joint. A spherical joint is a 3 degree of freedom joint. So it subtract 3 only position. It doesn't constrain any angles. What else do we have? We have a universal joint. that only allows 2 degrees of freedom, 2 rotations, but constrain all other degrees of freedom. And the list goes on. So this equation, one thing I wasn't planning to mention, but it is, it may not be always accurate. So a good example is this system. I have one joint here, one joint there. Okay, actually that could be a good exercise. Let's do this. So I have this system. So I have 1, 2, 3 bodies. And another body being the ground. So this is body, this is being the ground. So essentially I have 4 bodies. Let me see. Am I doing it right? No, I don't need to consider that. So this is called 4 mechanism because the ground is also considered an object. Oh, that would actually be nice. So it's in 2D. I have 1, 2, 3, 4 bodies, each of them 3 degrees of freedom. That is the total degrees of freedom if all of them were floating in a space. Now let's add the joints. So for body number 1, 2, and 3, I have pin joints. I have 1, 2, 3, 4 pin joints. And each one of them subtract 2 degrees of freedom from the system. And one other thing I didn't mention, this body 4 is more or less welded to the ground. So let me add this. Weld joint is reduces all degrees of freedom. So 3, I'm struggling, -3. And in case of a rigid body in 3D, it subtract all degrees of freedom from the system. So I have one of these weld joints that subtract 3 degrees of freedom. So n is 12 minus 8 minus 3 equals 1. So that's a 1 degree of freedom system. One thing you can do, let me add another example here. Let's extend this joint. So this is one body. Let me add this. So it's still body number 2. I'm not adding anything. I'm not going to worry about number 4. Let's add number 5. So all the grounds, let's assume it's just one body. Now I have 5 times 3. This is a pin joint 2. Minus, I have 1, 2, 3, 4, 5, 6. 6 times 2. Again, minus maybe 1 times 3 for the ground. So how much is that? That one is 15 minus 12 minus 3 equals 0. So that's kind of curious. It is mathematically correct. But something to remember is that this equation does not take into account the shape of our mechanism. So if all these links are parallel, we know that the system can move. In practice, it has 1 active degree of freedom, but it doesn't show up here. And the discrepancy is that the system only works if all of these links, link 5, 1, and 3, are perfectly parallel. If there is misalignment, or if I have my joint my link in such a way. It's the same mechanism, but now the system doesn't move. So as I want to turn this point just prevents movement. So this equation can or cannot be correct given the actual shape of your system. And it works in most of the time that we are not documenting special cases. Okay. So that is the idea of constraint, the general idea of constraint. I'm going to need another slide actually. Let me stop this. How do I do that? Ensure. Keep. New slide. So a very important classification of constraints. We are dealing with kinematic constraints, right? Oh no, that's black. You're dealing with kinematic constraints. And kinematic constraints can be categorized in two general categories. One category is called holonomic constraint. This is not an M, it's IN. Constraint. Holonomic constraints are those that are fundamentally at position level. Level. What does that mean? A pin joint, for instance, we talked about pin joint. So I have this object pinned to another object. Well, no, let's actually do another example. So I have this freely moving particle, and I pin it to the ground. So before I could describe it by coordinates x and y, but now I have added a joint to the system, and the joint acts at a position level because this x minus position of like x of O, let me call it this way. No, let me. That's right. X of O. This is point O squared plus y minus y O squared equals this distance squared. So this is a relationship, let's call it phi, between positional variables. You can write it as you can take derivative of it and write it as some velocity functions, but note that you can always scale it down or go back in derivatives and reduce a constraint to a position level function. So this is what we call holonomic constraint, and most of the joints in the machines that we have are holonomic constraints. So a spherical joint, pin joint, universal joint, slider joint, all of those are holonomic constraints. Another very important class, which is fundamentally different, are called, you guessed it, or no, go back. Non-holonomic constraints. Constraints. So many dots. So these constraints are those that, don't do this, please. At least one constraint or at least one equation in the constraint equation, or fundamentally the constraint itself, is at velocity or differential level and cannot be reduced to position level. Okay, it is weird, the definition, but it is more easier to show it by an example. So let's consider the example of a wheel. So I have a wheel. This is my wheel. It's turning and going on a plane. So this wheel has a kind of constraint that is not as a position level. What we know is that wheel, at least when the constraint is active, we haven't broken the wheel. The wheel can only go in the direction of the wheel itself. So in other words, the wheel can never slide sideways unless it's sliding and it's no longer a wheel. So if I look at it from the top, this is from the top view. This is my wheel. It's turning. I know its velocity can only be in the direction of the wheel itself, or perpendicular to the axis of the wheel. And that is very fundamental. It cannot be reduced to a position level constraint. Only that it is active at the velocity level. And to show that it's not a velocity level constraint, I can steer my wheel. So that is steerable. This is the path of the vehicle, the wheel. I can go up and then come to any other point. So the position of the wheel is not constrained. It can be anywhere on the plane. However, the only thing that matters is the direction its velocity can take. And that is defined by the orientation of the wheel in space. So that configuration is, or that constraint, sorry, is what we can do with what we call a non-holonomic constraint. And if you want to mathematically write that, so this is again a wheel, and I'm looking at maybe XY plane. So I can, in principle, if the wheel isn't active, this body can go either in X and Y direction. So it can have Vx and Vy. But the property of wheel is that the actual velocity is only going to be along the direction. So if this is V, how do I write it? Let me think, what is the best way? So no, let me not show that. So if I map these onto the two directions that are normal to the wheel and perpendicular to the wheel. So I have Vx times the sine of let's call it theta, the orientation of the wheel, sine of theta minus Vy cosine of theta. This is the velocity in the normal direction. So this is the normal. What? See, my laptop is dying. 1 second, I get the charger. Sadly, the quality of the production value of these videos have dropped. Sorry about that. I hope it works now. Let's see. Clean up this one. I cannot clean this somehow. Okay. The velocity in the normal direction, this is 0. So you can see now my constraint equation is at some velocity level rather than the position level that we had before. So usually, let me finish this up. The holonomic constraints, we can write them as a function, usually a nonlinear function of the position coordinates and possibly time equals 0. The non-holonomic constraints are usually written as a function of position coordinates, the velocity coordinates, and possibly time. And that existence and non-reducible velocity terms is what makes a constraint non-holonomic. To be honest, the only one I know is wheel, and maybe another example is maybe a knife or a bandsaw that you can only cut in the direction of the knife or a saw. You can never cut sideways. To do that, you have to take a path to be able to reach it to another point. Okay, so it was not the best video, but I hope I could make it. In the next 2 videos, we will be talking about the idea of generalized coordinates, how we can combine degrees of freedom idea and constraint, and instead of working with individual coordinates of each particle or each body, we can have a generalized version of that, and how that forms a configuration space. So, all right, until then.